This video looks at situations that you've seen in the past. Situations where the forces are balanced, either up and down or left and right, or maybe even both. These situations are said to be in equilibrium. What we observe is that the system doesn't move at all, or maybe that the system does move, but it has a constant velocity, where the acceleration is zero. We're going to look at these from a new perspective where there is some mathematics in the problem. So this would be an example we saw in the past, an apple suspended from a string. That apple's not moving, it's in equilibrium. An apple at rest on a table. Again, anything at rest is going to be in equilibrium because if there's no motion, then there's no change to the motion, so the forces would be balanced. Or if the apple was being pulled with some sort of string, so there's a tension force, if there's an equal amount of friction in the other direction, the motion doesn't change. And so this would also be in equilibrium. We'll hit those a little bit more in a later idea. Mathematically, how we can say this is that the net force is zero, or sigma F is equal to zero. The symbol sigma refers to something very mathematical, where you add things together, but because of the little arrow above the F, we pay attention to the directions. And so it might be adding positive and negative numbers. We've seen this before. We would say that a situation like this is or we now say that it's in equilibrium. The net force is zero. The forces are balanced. Less formally, we might say the up forces are equal to the down forces. In the same way, if we have this sort of situation, we might say that the right forces equal the left forces. Remember the little hashtags, tick marks indicate that forces are equal in those two different directions. Let's look more carefully at the example of an apple that's hanging from a string. So, think about what sorts of forces are actually acting on that apple. The forces that are acting are going to be tension because of the string pulling up, and then always we have gravity pulling down. And we can use some symbols to represent those, F sub t and F sub g, or if you prefer to write out the whole word, that's fine too. We can also now represent this mathematically, kind of building off of that sigma F equals zero idea. So we could assign up the positive direction and down the negative direction, and we would end up saying just very simply that the tension force must equal the gravitational force. It's probably not a big jump for you, if that's what it means for two forces to have equal values. But this notation of putting all the forces on the left side of this equation, that's going to help us in later problems. So I want to make sure that you see that. Let's take a look now if we put some numbers into this. If the apple's mass is 0.16 kilograms, we should be able to figure out the tension in the string. To do that, we would first want to use that mass and assume that we're on Earth and calculate the gravitational force, or the weight of that apple. And in this case, we would end up multiplying by 10 and get 1.6 newtons. And then because we know it's in equilibrium, we know that that downward force would have to equal the upward force of tension, and that would give us our answer. Let's take a look at the apple on a table, an apple that's just sitting there. Again, think about what sorts of forces are acting on this apple. The forces should be the normal force and gravity. Again, gravity is always in there, but the normal force is what we call the force that a surface exerts on an object. And it would be upwards in this case. It is in many situations. And if the apple's not moving, those two forces have to equal each other in value, in magnitude. So we could write a similar statement, mathematical statement, that describes this. And in the end, we find, of course, that the normal force would equal the gravitational force in size, and we would be able to use that to solve some sort of numerical question. If the upward force is 0.86 newtons, that is the normal force. So what we need to do is understand that that connection is that number now also tells us the gravitational force. We now know what the weight of the apple is. And so we would rearrange our weight formula and end up dividing by 10 to find that the apple's mass is 0.086 kilograms. This situation has a slightly different setup. There's actually two strings that are supporting the ball. So let's think about how that would affect our calculations. First of all, we would still do something very similar in that we would think about there being an equilibrium, that the sum of the forces would be 0. So we'd want to really think about what forces are acting on this ball. And as we look at it, there's not just one string pulling up, there are two strings pulling up. And in fact, if we sort of think about it, they can't both be the same length of an arrow as the weight force. Because if they were the same length, then there would be twice as much force pulling up as there was pulling down. And so they're going to adjust. There's going to be less tension in each of those strings. It's not needed in order to support the full weight. If we write a mathematical statement that represents this diagram, we would see that there would be two tension forces up and just the one gravitational force down. Again, this looks very formal, but it's going to help us with later problems when things really start to move and accelerate. So mathematically, we could simplify a little bit and see that twice the tension force would equal the gravitational force pulling down. Another way of thinking about all of the up forces together would equal the down force, gravity. So we would need to know that gravitational force. We might go off to the side and calculate what that would be, 80 newtons, and then recognize that our tension force would be half of that number. So each string pulls with 40 newtons, so that the total balances the 80 newtons of gravitational force pulling down.